All right, so assuming everyone can hear me okay, we're going to get started. My name is Will. I'm a third-year astrophysics major, and I'm on the SPS board just like Viraj, and so I'll be leading today's session. So I'm going to start screen sharing the notebook. I highly encourage you to follow along because there's plenty of things you can mess with while I'm working or afterwards, and this is a sort of good introduction to how to work with data in Python, which will be very useful when completing a project for this course. And actually, one option for doing your project for this course is working on the same data set I'll show you today. So without further, I will start talking. All right, so hopefully everyone sees something like this if you're wanting to follow along. So today we're going to be talking about a little bit about NumPy, which we talked about last week a bit. And we're going to talk about pandas primarily. Pandas is the main, most important data science package for Python. It's how you deal with table data, and it's just ubiquitous everywhere. And then we're going to talk more about sort of how to make nice plots, and then mess around with some other scientific tools from other packages sort of to get you familiar with how to use them, even if you're not going to use these specific tools. All right, so to start off, we're just going to go back through a little bit of NumPy. So as you may recall, NumPy is short for numerical Python. And the main thing in NumPy is manipulating arrays. So in default Python, the main sort of set in the mathematical sense is a list. But it turns out there's a lot of things that lists can't do that arrays in Python can do. And so I'm just going to go through some of them because it's directly relevant to when we start getting into data analysis. So I'm going to zoom in a bit, so hopefully it's a little easier for you guys to see on screen. It's maybe a little too far, sorry. All right, so in Python, remember, this is how you declare a list. You have some numbers within a bracket stored in this variable. And likewise, to declare a NumPy array, you just need to import NumPy at the top of your notebook, which I realize I forgot to do. So if you're wondering why you're running into errors immediately, I'll fix that before we upload to the website. But this is how you declare a NumPy array. You can basically slap a list into np.array in parentheses, and it'll just convert your list into an array. So arrays are great because you can do a lot more math with them. So with a list in Python, when you do your list plus a number, you get an error. It says you can't add an integer to a list, which sounds really inconvenient, right? Because it should be trivial to add, 6 plus 1, 6 plus 3, 5 plus 6. But turns out it's not in basic Python. So in NumPy, you can fix that problem by just doing it with arrays, where you can just do the exact same thing, except with your array instead of your list, and voila, it does exactly what you would hope it do. So basic addition of scalars to vectors, or arrays in this case, is very simple. Same thing goes for other math operations. So squaring a list of numbers can't be done in Python. You get an error with the power operator and doing a list to a power. But in NumPy, the same thing is super easy. You can just do array squared, and you'll get the square of each element in your array. So these are all very useful properties. Likewise, if you wanted to deal with two arrays or two vectors, you can't subtract two vectors in default lists in Python. So when I run this, you're going to get an error again. Can't subtract a list from itself. So once again, it's this very, very simple operation you would hope you could do mathematically in Python that you can't do with lists. And once again, NumPy is here to save the day. A list minus itself is 0, 0, 0, 0, 0. Great. Same thing goes for defining arrays for a certain length and filling it with a value. So in default Python, the way you would have to do that with lists is you put a number inside these brackets, say 5, and then you put this star here times the length of your array. And so extremely confusingly, this is not multiplication. This just says take the element and duplicate it 10 times and make a list of that, which is extremely syntactically confusing. And if you're writing code for research or something, someone would probably scream when they looked at your code. So instead, in NumPy, there's a very convenient way to do that. You just say numpy.full. So to give you a brief reminder, when you call np dot something or scipy dot something or map.lib dot something, this is the package. or an abbreviation of the package in this case. And then this is the function from the package, which takes certain attributes within the parentheses. So here we're saying create an array of shape 10, so 1D array or 1D vector, shape 10, and fill it with 5s, and there you go. These two things do the exact same thing, except for one of them is entirely confusing. Some things in NumPy versus standard Python are a bit more similar. So in this one, this sort of example cell, I'm trying to sort arrays, just ascending sort. So if you define your list and you call sorted of that list in parentheses, you'll see it lights up like a keyword in default Python, and it'll sort your list into another list. Very simple. In NumPy, it's basically the same thing. It's just np.sort. One thing you sort of don't see is behind the hood. You can actually call various attributes of np.sort, which might be useful. So for example, I believe it's, let me show you actually. So calling a function like this in Python with a question mark after it will tell you a little bit about what that function does. And so you can see that you can actually change which sorting algorithm it uses, which could be useful for more advanced applications where your speed is very important. You can change axis. So if you're sorting a 2D array, you can have special things. And you can also do a bunch of other fancy stuff that you couldn't do with the default sorted in Python, but ultimately they're rather similar. So then a main use case of NumPy that lists can't even do at all, practically, is to deal with matrices or multidimensional data. So I realize I'm going very fast because this isn't meant to be the main focus, but I just want to give you a little taste of why you would want to use NumPy so that makes sense when we start talking about how to analyze tabular data. So let's say we want to create a 3x4 matrix. Okay, well in NumPy, you can just say np.zeros or np.full like we used before. You can say give it a shape of 3 rows and 4 columns, and you get, great, you got 3 rows and 4 columns, all sort of in a nicely nested array. To be honest, I've done plenty of Python for years. I still don't know how to do that with lists. So it's much, much simpler to do things with NumPy when it comes to multidimensional data. So what if you want to do a 3x4 array instead? So if you've done a bit of linear algebra or just algebra in some places, then you'll know that there's something called the transpose of a matrix, which is just saying take the ith element, the ith jth element, so an ordered pair ij, and just flip the indices. So you're basically flipping about the main diagonal. And so you have your 3x4 matrix. You can just call matrix.t, which is short for transpose, and voila, you get a 4x3 instead, which is exactly what we wanted. So 4 rows and 3 columns. And equivalently, you can say np.transpose. So if you want your code to be readable, or you want this to work for very, very large arrays, NumPy is really great. I guess that's a good time to mention NumPy excels at fast operations. So anytime you can do anything with a matrix or a vector in NumPy, or array in NumPy is the same thing as a vector, I guess. It's much better to use NumPy, and that's because it's built in C and Fortran, which are just faster programming languages. So what you're not seeing behind the scenes is a lot more careful programming behind the scenes, which are making things faster for you. If you want to do matrix multiplication with NumPy, you just create your two matrices. So here I create the identity matrix. So that's just a 1 in the first row, first column, and a 1 in the other last row, last column. And if you had a larger matrix, it'd just be all the way down the main diagonal. And then if I want to create just sort of random numbers and make them into an array, one thing I can do is generate 4 random numbers. And using NumPy, I can reshape those into a 2x2 matrix. So this is saying basically, if you have some long string of numbers and you just want to collapse it into a grid really quickly, or if you have some predetermined scheme you want to do it with, you can just call reshape and then give it the shape you want. And magically, your 4 random numbers nicely fit into the array you wanted, so 2x2. And then to multiply that times the earlier array, you can just very simply call np.matmul, which is short for matrix multiplication. You put the first matrix you want to multiply, and then the second one, recalling that actually order matters, and it's not commutative for matrices. and take the product, and you get exactly what you expect from the identity matrix. So when you multiply something by the identity matrix, you end up with that matrix again. So great, works, and it's especially useful when you want to do larger matrices. And this can come up if you want to do equation solving in Python, for example, where matrices are often a very good way to do that. So I realized that was all super fast. And I'm sorry that we have limited time together, otherwise I would go slower, but this is all in the notebook. And if you want to explore it more, I highly encourage you to do that because that's a really, really useful thing to be familiar with in Python. Moving on. So today's sort of main focus is going to be about pandas. So I'm afraid I don't have a good reason why it's called pandas for you, but it is sort of the most important package you need to know for analyzing data in Python. And so it's extremely flexible. You can load files in from almost any format, given some, the right commands. You can do column operations, row operations. You can sort your table. You can plot from it. It's multifaceted and extremely useful. So in reality, pandas is just built on top of something called record arrays, which are a NumPy feature. So really what pandas are doing are giving you sort of a nice user interface for sort of more complicated behind the scenes that's going on with NumPy. So when we're dealing with these matrices up here, okay, sure, you can plausibly see how you'd make a table from these. But it can get rather complicated. First of all, what if you want to have columns, column headers rather, in your matrix? You can't have multiple data types in an array in Python. So you'd have to go to something called a NumPy record array, and those start to get complicated, and you have to be very careful about the way you handle it. So Pandas sort of helps remove some of that ambiguity and makes it much easier to work with these sort of behind-the-scenes powerful NumPy arrays. So as usual, to import a package, this one called pandas, you just call import pandas, and it is, you'll be hard pressed to find a single person who doesn't do import pandas as PD. So just like NumPy, everyone imports it as NP, and matplotlib.pyplot, which everyone imports as PLT, the sort of shorthand for pandas is PD. And so that's just an abbreviation. And then here I'm just importing sort of some bad practice, which is filtering out warnings that might come up with when you run some of the cells. And there's one particularly common error in Python that I'll point out later, or a warning that comes up in Python that just can become annoying even though it's not really an issue. And so that's why I have it here. So pandas is built around something called a data frame. So data frame is a record array with some extra features. And so it's basically a table that you can throw any data type into, and you can have columns of different data types, which sounds like something that would be super easy to implement, but NumPy arrays don't do that by default. So if you want to have a column of integers, great, you can have that. You can have columns of trues and falses. You can have a column of names. You can even have a columns of empty values if you really wanted, which turns out to be very useful when you're working with data where some of the columns might be incomplete, which is another big advantage of pandas. It makes it sort of easy to deal with those. So there are sort of two main ways to deal with data in Python. You can either sort of create it by hand into a data frame by coming up with arrays for each column, and then there's this sort of call pd.dataframe, and you can give it the data sort of individual arrays and the list of columns, and it'll sort of throw it all together for you. And in practice, that's good to know how to do, but in reality, you probably won't see that very often, because if you're working with astronomy data, physics data, chemistry data, you're almost certainly going to be passed someone's data file, which some instrument has spit out from some automatic pipeline or something like that. Or you're downloading public data from Atlas or other certain experiments. So that I'm going to focus on importing data from those kinds of sources. And so you can do it through this function called read CSV in Pandas. So pd.read CSV. For those who aren't familiar, CSV stands for comma separated variable file. And so if you want to look at what's inside a comma separated variable file, it's really, really simple. If Zoom will actually let me screen share. Okay, you'll have to take my word for it. Or sorry, move to a different tab is what I meant. Basically, you just have a list of column headers at the top separated by commas, and then every single data point in your array is first row, first column, comma, second row, first row, second column, comma, and you just have all the data points separated by commas. It's really, really simple if you open this file up on your computer. And so one of the convenient things about pandas is that you can actually boot these files open from a website. So here I've just put the file on my GitHub that we'll be working with today, and you should be able to directly call into this link to see this file. And if you can't, please let me know. I'll be happy to deal with it on the fly. So the data we're going to be working with in this file is data from the NASA Exoplanet Archive. And so this is a recent-ish file of all the known and candidate exoplanets that we know of. So there are quite a few of them, and we'll figure out exactly how to tell how many there are in a bit. So here is what it looks like when you open up a pandas data frame. So pd.read.csv automatically does the creation of this data frame idea, and you can store it just like any other variable, and then the variable is an object which has some attributes. So those attributes are what you're working with when you're working with the pandas data frame. So the most immediately useful one is head. So data frame is usually abbreviated to DF, so I'm calling the DF object's header, basically. And what that does is it just shows you the first 5 rows and most of the columns that can fit, and that's it. So here's this data set. These are all the variable names as you'd find them on the NASA website. So we've got planet name, discovery method, whether the discovery is considered controversial and perhaps fake, orbital period, this time in days, orbital semi-major axis in astronomical units. You've got eccentricity of your orbit, so how circular it is. You have inclination, so at what angle relative to the observer it is. You've got the planet mass, and then sort of towards the end, you get details about the star where these planets are orbiting around. So recalling that, the main problem with detecting exoplanets is that they are basically small reflective objects against a very bright star. We can only detect them at around very bright close stars. And I'll explain a little more why that is too in a minute. And so this is just telling you that the magnitude of the star that you find the planet around is 4. And so if you know a little astronomy, you'll know that you can see stars with the naked eye up to about a magnitude of 6. And as the magnitude gets bigger, stars become fainter, confusingly. So these are bright stars, and this is just sort of an introduction to what this data set looks like. As you can see, though, the columns are kind of cut off. So if you wanted to see all the columns in your data set and print them out, you can just call df.columns, and it'll give you all the names of the columns in the sort of index object, which you can think of as plus or minus an array. And there's some reasons why you would want to use it like an array later, like if you want to loop through columns or something. To figure out how long your data frame is, you can simply call print len df. So len is the same function you would use to find the length of a list or an array, and it still works for data frames. And you'll see that it's 4,284 planets, which is very recent estimate. I think this data would have been updated within the last month. So we're dealing with the cutting edge data here. And then if you want to equivalently call len df.index, this is another way, which is sometimes a little more reliable to figure out the length of your data set, because sometimes there can be issues with calling it the first way. So I want to pause here and ask whether there's any questions before I continue. Anything in chat, Viraj?
No, nothing there.
Okay, cool. I'll wait 10 more seconds in case anyone wants to speak up. All right, pushing forward.
We have a question. Is the length the number of rows we hear? Yeah. Is the length the number of rows?
Yes. Good question. The length is the number of rows, and then as you can see sort of above, there are 30 columns in the data set. So this data set is essentially a 4,284 by 30 array, and we're seeing this kind of convenient user interface you would only get from pandas. So if you wanted to look at the disgusting NumPy way of doing it, you'd see nested arrays all over the place, and you'd see confusing comments about data types and something called tuples, which Viraj talked about last week, and it can become complicated. So this is sort of the very convenient way of looking at your data quickly.
There's one more question.
Sure.
Does the length include the header row?
It does not. Good question. Was that from the chat?
Yeah.
Great question. Yeah, it does not, which is convenient. Pandas is smart enough to automatically detect the header row in a CSV file if you've constructed it correctly. And if for whatever reason you have comments at the top of your file, which you may very well when you download the data, rather than deleting them out of the top of the file manually, which I've done many times, you can actually do skip rows equals 1. And if I did that, then we would skip over the header row, and pandas would get really confused and start thinking that this first row is the header. But yeah, no, that does not count explicitly the column header row. Great question. So to continue. So one of the most useful things about doing things with pandas is that to get a single column of data is really, really easy. So all you need to do is call your data frame name, which is df here, and then a bracket, and then the column name, and then close bracket. And so this bracket notation is meant to be distinguished from sort of parentheses notation. So generally when you see parentheses in Python, like if I just did print up here, I actually need to run the code. And you see it loads in pretty quickly, by the way. 4,284 is not big for a data file, and pandas can certainly handle that. So when you see parentheses in Python, that generally means function. So in NumPy, when you're doing indexing or looking at columns, you'll see everything with brackets. So here I'm just saying, take the planet name column from the data frame. And so you'll see two things when I do this. You'll see this row of 0, 1, 2, 3, all the way up to 400, 283. That's called the index. And then you'll see the planet names, the data values. And so one of the very convenient things about doing it this way is that sometimes you want to loop through the index. That can be very convenient. So when we're doing print len df.index earlier, we were really just counting how many numbers are in this. Great. And so if you're wondering where these names come from, by the way, planets are always names with lowercase letters. The middle 3 digits is an abbreviation for the constellation. So this one is Gemini, this one's Andromeda, this one's Coma Berenices. And then usually the Greek letter name in front of it is a vague approximation to how bright the star is based on how it compares to all the other stars in that constellation. But these were all assigned way before modern telescopes. So, and like before anything was systematic. So oftentimes the alpha star, which is supposed to be the brightest, will not actually be the brightest. And stars change brightness over time, which makes that even more confusing. But that's where the planet names come from, if you're wondering. So if you want to just get the data values, rather than the values plus this index row, you can literally just call column name dot values. And it returns an array with the planet names, and you'll see that these are objects because each of these is a string, which is just a list of characters in Python, and strings are objects. Same thing goes for numerical data. And I guess this is a good time to mention the formal name for what you just saw before I called values is a series. So a series is just your values plus an index plus mention of the data type. And so once again, if you just want to look at the values for orbital period, these are all in days. You wouldn't know that based on this data alone, but trust me, I looked at the documentation. And you'll see, great, you just have a very generic NumPy array of your orbital periods. And say I want to take the first one, I just call 0, and you'll get, great, the first row's value for orbital period is 0. Seems fairly straightforward. So just like any other NumPy array, this is just one giant NumPy array, and you can index it with 0. If you wanted to take every other value, you could just do like this, and you're take the first value, the third value, et cetera, et cetera. You can display these in reverse by calling -1, et cetera, et cetera. Just like any old NumPy array, which is a very, very important point. Pandas is built on top of NumPy arrays, and that is why it's nice. And so, the stuff we're talking about with lists versus NumPy arrays becomes very useful here. So let's say we want to square a column in our data frame. If you wanted to do that, you could just create an array by copying a NumPy array here from the orbital period column. And copying just prevents you from editing the original data. So if you're ever worried you're going to edit the original data, it's a good idea just to create a copy. So I've created this variable orbital times, and I want to say square all the values within that orbital period data. Great, it works. All you have to do is orbital times squared. Sorry, I need to remember to run cells. That's it. It's very, very simple. So you can imagine that there are plenty of reasons why you'd want to multiply every data element in your data to get a new set of values. So if you want to do a unit conversion, for example, to do a unit conversion in Python, all you would need to do using pandas is to say orbital times days equals the orbital periods column, which is this, times, or sorry, these are already in days, orbital times years, and then you just divide by 365, and that's it. That simple. That's one of the reasons why people love pandas, is that this is just such a convenient way of manipulating data. And so now if you wanted to create a column based on this, so what if you wanted to make orbital times years into a column? So you had the column data for that. You could just say df orbital times years equals orbital times years. It's that simple, right? You're just saying, take this NumPy array you've already defined and shove it into this new column. So this is just like, if you think of this as like x equals 6, this just acts like a variable which happens to be part of your table, or your data frame in this case, and assign it these values. And you can actually make this even faster. You can condense these into one line. So you could just say orbital times years is orbital period column divided by 365. So you can create columns from other columns very simply. And this is perfect use case for it, creating unit conversions. And so to emphasize the points I was making earlier, you can't do that with lists. You can't just square a list. You can't add 6 to a list. You can't do any of that. So pandas being built on top of NumPy is extremely useful. Another extremely useful factor related to these columns we've been working with is that if you want to calculate the mean or median or any kind of other statistic, or the maximum or the minimum, it's really simple. You just call np.mean and then the column. It just acts like any other array. And you could also call np.mean, orbital times as we've done up here, but that's an extra step you don't need. So you can just do np.max, your column in parentheses, np.mean with df of your column in parentheses. Really, really simple. You can see, why this would be useful for doing data analysis. So I'm going to pause for another 10 seconds for questions if anyone has any.
Does this kind of thing work the same way for rows? Or I guess
oh yeah, that's a really good question. No, is the short answer. It is not that convenient for rows. And I think if we have time at the end, I'll show you how to do it with rows. You'll have to use sort of more complicated functions, basically. But yeah, no, it's much easier to work with columns and pandas. But you definitely can do manipulations with rows, just like you would in an Excel spreadsheet, like summing a column. Right. So if you wanted to do that, though, one way to do it is actually I'll get back to this. I'll get back to this. But okay. Good thinking. It's not as simple. Okay. Yeah. So as I just showed you, Pandas has a really, really good advantage that you can just create new columns by smashing an old column and some factor. So here in our data set, B mass J is the planet's mass in Jupiter masses. So as if you just figured out how many multiples of Jupiter's mass is your planet. And sort of as a fun fact about exoplanets, there's a whole class of exoplanets called hot Jupiters, which are at or above the mass of Jupiter, but orbit super close to their sun. So we're actually kind of unique among exoplanet systems by not having a planet like that. because we don't have sort of these massive gas giants until further out. And so here's how you do that unit conversion again. I recommend you try other ones just for fun. But I'm going to move on since I'm going slowly and I need to hurry. Okay, I'm not going slowly, I'm going quickly, but it's still need to hurry. Sorry about that. Okay, so another key point is that pandas columns act as NumPy arrays, as we've said, which makes plotting very easily. So if you had a NumPy array 1, 3, 5, and 2, 4, 6, all you'd have to do is call plot.scatter and then 1, 3, 5, 2, 4, 6. Same thing goes with pandas columns. You can just say plot this column versus this column. It quite literally could not be easier. So orbital period and mass are two ones we'll care a lot about throughout my talk today. So running that code, voila. So here are some quick highlights of the plotting functionality too. So once again, we're using matplotlib, which is sort of the standard Python plot. And you can do a bunch of things to make your data look nice. So you can set the Y limits and X limits. You can set the scale of the Y-axis and the X-axis to be logarithmic, so in powers of 10. You can label your axes and set the font size. You can put a grid, as you can faintly see, and you can change how dark that grid is by calling alpha equals a number. You can change the font size of the actual numerical values. You can add a title. All that, I highly encourage you to mess around with for yourself. I won't go much more detail into that. And so looking at this data of period versus mass, you notice anything? You see how there's 3 different groups? That's sort of a curious phenomenon that we're going to kind of look at throughout this notebook. So what I will say is that it doesn't necessarily correspond to physical attributes of these planets, but it does correspond to, oh, sorry, I can't see chat. It does correspond to detection biases also. And so we're going to sort of explore that using pandas slicing. So what happens if you want to see part of a data set? So let's say we want to look at just these 2 clumps of data over here. You could say, okay, let's draw a line at 10 squared days, 100 days. So in Python, with pandas, that's really simple. You just say create, or just compare every element in your column to some number, which exploits the fact that you can do this with NumPy arrays and lists in Python, and save that as like a cut, which is essentially just a list of trues or false values. So when I do this, you say, give a value of false to every planet greater than 100 and give a value to true of every planet with period less than 100. And then if you want to actually create a subset of your initial data frame, so if you want to just use all the convenience of having a smaller data set, you would just call new data frame is your old one, and then in brackets, you call this true or false array, and it'll just automatically select only the elements of this array that were true. So if you look at new df, it's going to be identical to the old data frame. So it'll have the same columns and same order, except you've removed all the observations where period was greater than 100. So you've removed all of these things. And you'll see that the length of our data is still now 3,429 rows. And there are still the same number of columns, remembering that we defined a new column up above. So that added one. Alternately, if you want to do the same thing, except you want to say, take all the planets with periods greater than 100 days, you could either flip the sign on this equality, or as is sometimes very shorthandy, you can just call this little tilde mark next to the same trues and false arrays, and it'll just reverse the operation. So if I look at this data frame, you'll expect that this one will only have 1,900 1,900 rows because you've thrown out, this is just the header. And then if I did len new df 2, you'll see, I did the math wrong, but yeah, I did the math egregiously wrong. Sorry about that. You'll see that the new data with greater than 100 is much smaller. And so that's sort of a very convenient shorthand. And I'm going to have to keep going, and I'm sorry not to be able to address any of these in more detail, but this is a very, very useful feature. If you want to select one type of planet or one type of star or one type of particle if you're doing particle physics. Really useful stuff. So with this slicing functionality, we can sort of explore features of our data. So one thing that's really useful is if you have a row where you know it can take only certain values. So say you've given all your data a label, a label A, a label B, label C, label D, label E. But you don't know exactly what those labels are. Like what if there are 100 of them and you don't know all of them? And you don't want to just simply call that column because you'll find 100 copies of each value. What you can do is you can call np.unique and then your column name. And what that does is says takes this column and find all the unique values and store them in an array. So rather than printing astrometry, which is one discovery method that this column stores 100 times, you've just scored it once. And if you tack on this return counts equals true, you can see how many times that method shows up in your data. And so now is a really good time to talk very, very briefly about what these discovery methods are. So for exoplanets, just as a preview, there are sort of two dominant methods for finding exoplanets. One of them is so-called radial velocity method. And unfortunately, I'm not sure I'm going to be able to change tab to show you the link I wanted to show you, which is frustrating, but Zoom just doesn't want to do that for me. That is not what I want to do. But essentially what radial velocity method does is that it uses the fact that planets pull very slightly on their planets. Planets pull very slightly on their host stars. And so the spectrum of light from that star is Doppler shifted. And from that Doppler shift, you can say, oh, there must be a planet of this mass causing that level of shift. And then the other main method you can find exoplanets with, there's many methods, but these are by far the dominant two, is transits. So transit is just like an eclipse. What happens is a planet will pass in front of a host star, and assuming that the planet's orbit is sort of edge on, so it's orbiting around our sight, our sight line looks straight at its orbit parallel, or at only a slight inclination, then you should be able to see a dip in brightness from the star. And from that dip in brightness, you can say, oh, there must be a planet of this size. And then you can figure out how long its orbital period is from how long that dip is and how long between dips there are. And so if I wanted to select different groups of data that fit each of these discovery methods, you could create a new sort of truth value array like we did before and say, take all planets with a discovery method of radial velocity or microlensing, which is what happens when light is very slightly bent by these planets, or imaging, which is very hard to do with exoplanets, but actually being able to photograph them directly, and then transit again. And so you can create these new data frames just by saying, take all values with this method or this method or this method, this method. And you'll see by far the number of transit planets is the biggest. And then you'll see that the number of transit or radial velocity planets is second. And so that's sort of what we know to be true about exoplanet discoveries. And so if you want to plot each of them separately, now that you have individual data frames for each, you can do that and you get this very nice plot. And I encourage you to take a look at the plot and see whether you understand everything that's going on in the cell. I won't explain it now. But you can see very clearly that these three groups seem to have some very clear correlation with discovery method. So all these red planets were those discovered with radial velocities. And the code for sort of distinguishing these is here, and I encourage you to check that out on your own time. And so each discovery method has different pros and cons and parameter regimes which it can probe. And so one problem with transit method, which is the blue here, is that transit probability is really low when the orbital period of these are really long, and it's really hard to find them. So if your planet only goes around its host star once every 10 years, it's pretty unlikely that we've discovered you yet, because we've only had exoplanet detecting telescopes for a certain number of years, and it takes a certain amount of passes around its host star for us to be confident that it's a planet. So you'll find very hard to find long period planets with transits, even though in principle there should be no physical reason for there to be a gap here. And so if you wanted to say, instead take all planets that are either radial velocity, so using this sort of subselection here, or via transit, you can actually combine these sort of truth values like this. You can say, find the radial velocity truth array and the transit truth array, and use this operator called OR, which will return true if either of these are true. So this is saying create a new data frame of all planets that were discovered via radial velocity or transit. And that's how you do that in Python. So if you wanted to do sub-selection based on multiple categories rather than just one, that's how you do it. I'm going to skip over this because I think it's very straightforward, but if you want to just plot a histogram of a certain variable, it's very similar to doing the scatter plot above. You just call plot.hist, and then your favorite column, and you get a histogram. And so here I've done some log scaling and things, and I encourage you to check that out on your own time. And I'm sorry for lack of time, but that's how you do that. So sort of to tease you a bit about final projects you can do with this data, if you're interested in doing that for this sort of workshop series, here are some interesting things you can look at in the data. So if you're familiar with the laws of physics, which I assume many of you are, in mechanics, there's something called Kepler's third law, which basically relates the orbital radius or semi-major axis of a body orbiting a larger body to its orbital period. And so this was actually used well before Newton sort of threw down F equals ma onto a piece of paper. And it's sort of a great way that Newton's gravitation equations can be verified. So Newton was heavily influenced by Kepler, who came up with this relationship or discovered it from looking at the planets. And so in a very convoluted universe where it's easier to track planets around other stars than it is to track your own star, so maybe if your own star doesn't have any planets other than the one you're on, you could potentially derive the laws of physics using just this exoplanet data. So if I'm plotting orbital period versus semi-major axis, and I'm just applying some data cleaning here, I wouldn't worry too much about it. But you can sort of see how we're using techniques from before. You can see that there's some kind of physical relationship, and you can maybe plausibly claim that there's a line to be drawn up here. And so we probably want to just throw out this data point. So we can place a cut just like we did on 100 days earlier for orbital periods, and say take everything less than 1 million day orbital period. And so I do just that here. This is creating a new data frame and making those cuts in one line. So you call df and then the bracket, and then each of these are truth statements. So take all data with orbital period less than 1 million and orbital period greater than 1,000. And these two here just say, make sure the data is finite. So make sure the values aren't not a number, or NaN in Python, or a nan as you'll sometimes hear it called. So that's what that's doing. And then plotting it again, you see we've thrown out the huge outlier and we only have sort of this data point here, and the physical relationship becomes very clear. And so you might say, oh, that looks like a square root function or something. And you'd be close. And so the best way to look at that kind of relationship would be to look at a log-log plot, which has a slope equal to the power of the relationship, in case you didn't know that. And so if I now take the logarithm of each of those columns, so create a new column that is just the log of the old column. So log of the orbital period and log of the semi-major axis, which is this variable S max, semi-major x. And then plot it again, you'll see this beautiful linear relationship, which is just screams power law. So something, orbital period to some power is your semi-major axis. And so you might say, how do we figure out what that power is? And as I'm sure you could guess, the easiest way to do that is through linear regression. So fitting a line to this data that minimizes sort of the residuals against that line. And so I apologize for going extremely fast, but I've kind of pushed myself up against the end of the session already, unfortunately. But to find the slope, here's some really useful scientific packages you can work with. So SciPy is one of them, and another is scikit-learn. And so scikit-learn, sklearn is very good for machine learning. That's a very advanced use case, but it also happens to have one of the more convenient linear regression options in Python. So from scikit-learn.linear-model, import linear regression, seems straightforward. You can just define sort of this one-dimensional array from your period data that's reshaped into the format that this package wants you to do it. So if you had just not reshaped it and tried it with the column, you would have found an error telling you exactly to do what I've done here, which is add.reshape -1, 1. So don't think this is some magic. Just know that if you had tried this on your own, it would have told you what to do. So it's very intuitive. Then you can define this sort of linear regression object. And so it's very simple. You just call linear regressor equals, or your favorite variable name equals linear regression. And I'm telling it to fit the intercept. And so this creates another object in Python. So just remember, objects are these sort of multi-tools that have attributes and functions associated with them. Just like a data frame is an object, this linear regression is an object, and it has some properties which you can access when you need them. And so given our data, which I've called x and y, you can say linear regressor.fit x and y, all very straightforward. And then .predict x. And so I know I've thrown a lot of lines of code here very quickly, but I just want to emphasize, like, when you're doing research coding, like what Viraj and I do, we don't know all this stuff coming in. Like when you have a problem you want to solve, you just Google how to do linear regression in Python, and you find the first reputable result, and it'll tell you to go use scikit-learn's linear regression. So you'll find stuff very similar to this online. And so that's sort of why Python is nice, is because people have made all these packages which can solve almost any problem you could possibly want. And so doing this, you get my slope estimate, which is an attribute of this linear regressor object. And it tells me that the slope here is 0.64. So recalling what we were talking about earlier, which is that the slope of a log-log plot is the power that relates the x and the y-axis. What we've said here is that the orbital period to the 2/3 power is the, is it the 2/3 or the 3/2? One of those two is the other variable. And so Kepler's law is period squared equals radius cubed. So in this case, period was on the, so it should be 2/3. T to the 2/3, so orbital period to the 2/3 equals semi-major axis. And from our data alone, we found 0.64, or 0.65 if you round, which sounds like a pretty good fit to me. And thus, if you wanted to plot the result, you could just call this predicted y values, which is just an array on its own, versus your initial x values. And you'll find that our model gives you this very nice linear fit to the data with slope 0.64. And I think all of us would agree that this is a pretty good fit. And mathematically behind the scenes, it's optimized this fit so that you can't shift it up or down to be any better. So it's minimized the sums of the squares of the residuals, so how different the model is from the data. So this is what they call ordinary least squares regressions behind the scenes. And so all of this stuff from here on is honestly probably too complicated to do real justice for me now. So I'm going to pause and ask for questions, and anytime we have after that, I'll see what I can do with this remaining stuff. So any questions? I know I just gave you a huge amount.
There's a question in the chat. So it's asking, what does the reshape bracket -1, 1 do?
Yeah, okay. That's a great question. And to be honest, I'm not entirely sure, but I can show you the before and after. So if I call x, you see what it's done is that it's converted it into a column of individual 1-by-1 arrays. And I could not begin to tell you why it does that. But this is how whoever coded the linear regression wanted us to do it. And so I think the other way you could do reshape -1, 1, I believe it's equivalent to the transpose, which I guess answers your question. So if I do, okay. So if I reshape -1, 1 and then transpose that reshaped data, you get the original column back. So I believe reshape -1, 1 is effectively identical to doing a transpose of the data. So rather than turning it into one row or one column with hundreds of rows, you've turned it into, it was originally one column with, it was originally one row with hundreds of columns, and now you've reshaped it into, okay, I'm just tripping over my words. Just know that it's effectively doing a transpose, and that's what the program wants you to do. Hopefully that's a good enough answer. Any other questions, Viraj?
No. Also, yeah, just as a point, like we will like talk about like this stuff sort of again on Friday, so that you know that it's not like just a one-time thing. Like you see it and then boom, it's done. We will talk about this again more on Friday. So
Mhm.
don't worry if you like don't understand a lot of
Yeah,
things.
yeah. Yeah, absolutely with Mirage said. And I just want to put all this stuff out here because I know we have very limited time with these workshops, and that when you're doing your final project, it may be useful to reference this. So
Yeah.
if you don't understand all the details now, you can feel free to message us over Slack or email and ask us questions about it. And remember that this is a resource for you to come back to, this video and this notebook, when you want to try to do these things, because I'm sure you'll want to do some kind of regression or advanced plotting or how to deal with data again when it comes to your final project.
And
Okay.
also like a big part of coding is just like looking at actual code and see like what is actually happening. Like that's how you learn actually. Like at least like that's how I learned. Like just looking at actual code and just see what it's doing.
So while we have an extra minute, I just want to tell you a couple more useful things you can do. So what we did here is that we had just used X values to predict Y values, right? In log space. So if we wanted to just convert these back to the non-logged values, you can just do 10 to that power. And to undo the reshaping, which I guess is directly related to your question, I'm calling the transpose of both data sets. So I'm undoing the reshaping, as we just said, and then I'm sorting the values just for convenience later on. And so doing that, you get this blue curve versus our original data. So this is our Kepler's law. You can say some things about this. It seems like it doesn't fit these exoplanets very well when you get to large orbital periods. And so one thing sort of curious about that though is, it can be very difficult to get accurate period measurements if there are multiple planet systems, for example. Recall that our model is also 0.64 power instead of 0.66 power, so you might expect that as you get to larger x-axis values, the model becomes more and more inaccurate. And then remember the error bars on these are probably big. So all things considered, it works pretty well in the low orbital period regime. And then if I want to show you one bonus thing, which might be very useful for Viraj's talk on Monday, is how to actually get values for any arbitrary value along outer power law. So one way to do that is just create some mathematical equation with the slope and say, great, apply this slope or this power to get a y value given an x value. But in reality, there's a better way to do that if your model is more complex, and that's through interpolating this function I've defined here. And so just like the linear regressor object, you can go into the SciPy package and import this interp1D object. So a 1D interpolator. And you can give it your x value and your y value you want to interpolate from. So the comparison here is to the linear regressor.fit. And so just saying interpolate based on your x and y values. And so interpolate, for those who aren't familiar in this context, means just add in lots of data points in between existing data points. And so if we do that, we can generate, sorry, I skipped cells again. We can do create an object called interp function, which is just the interpolated data, and then you can apply that like an f of x black box. So like if you have a function f of x, you give it an x, and f of x is the y value. So just think of it the same way here. This function, interp function, is your f. You're calling it on some simulated data that is very finely spaced, which is through this linspace command you saw last week. And then you have your simulated y data. And so when I generate this, we have all these data points we can work with in red. So rather than just being limited to points where we had previously regressed over, you now have a way to get the value of your model at any given x value you want. So if you want to do it at just a single x value, you just call interp function, which is your f of x of 10,000. and it'll tell you that, great, the orbital semi-major axis in astronomical units is 8.9. So you can check that correspondence, 10,000, 8.9 seems pretty good to me. Or 20,000 for a more illustrative example. Great, you call 20,000 and you'd see that it's 13 point whatever. And that is something that you didn't have a data point for that you can now find using your model. And then as a bonus exercise, I would see whether you can do this yourself. So plot your model and your data using the mathematical forms of things, and then see how accurate your model is by plotting the difference between the model I just showed you and your actual. So this is model minus actual, and then this is the same x-axis. And so what I think you'll find is that generally the model is pretty good. It's accurate where there's all these data points at very small orbital periods and gets less accurate as you go on. And so here I just leave you with a pitch. If you want to mess around with more with exoplanet data, perhaps look at transit data itself and see how much stars are dimmed by their planets, or investigate these 3 groups of planets more. You can feel free to sign up to be part of my group of mentees for our workshop, this final project this quarter. And I have time for final questions. I'm sorry this had to be so rushed, but the video is online and you can watch me on 0.75 speed if you need. But any questions?
Also, like, I can, like, stick around more if you have any questions later. So yeah, I think Will has another meeting, so he might leave. But if you have any questions, I can stick around and answer.
I'm just like wondering what like you'd recommend that we like look at by Friday the most.
Okay, so on Friday, I feel like, so the thing is, I won't be like building off of this. I'll just be I'll be sort of like talking about this in like a different context. So it's going to be more like a revision in a way. So I would just suggest us like, just going through this notebook and just like seeing like what sort of stuff we're doing and like how are we like manipulating data. So,
yeah. So Viraj, I think, is the one. Are you teaching this Friday, Viraj?
Yeah, Friday. Yeah.
Okay. So Viraj is the one who would know a little more specifically, but everything on here I include because I think it'll be useful for you in research. I mean, like almost everything I do in research is eventually plotted in Matplotlib. Almost everything I do in research uses, interpolate in SciPy, or it involves running regressions for curves that aren't necessarily lines, which I think Viraj will talk about a little more. And so getting familiar with messing around with data in pandas is, I think, fairly straightforward. If you spent 15 minutes on your own, I think you'd get pretty far. And you can use this notebook as a reference. And then for some of the more complicated stuff, I wouldn't necessarily worry too much about the details about this reshape. Like, it'll tell you when you need to do that. Like, you call a function and you don't reshape it and it'll call an error and tell you to do it. But knowing how to broadly import a package, many packages have this kind of object structure. I know Viraj will talk a little bit more about an example of this on Friday, using something called splines, which are curve fitting tools. Knowing how to do stuff like interp1d or linear regressor are very good to know, because that forms the basis of a lot of complicated Python functions. So in summary, knowing how to do plotting is very good and quick to learn, and then being at least vaguely familiar with how you might go about implementing these functions from other packages is a good idea.
Okay, thank you.
Any other questions before we want to run? All right, then with that, I'm going to run, unless there are questions in chat. But thank you very much for listening to the Rapid Fire Python. And Viraj can answer more questions if you have them.
Yeah. Thank you, Will. Yeah.
Bye, everyone.
Thank you. Bye-bye.
Bye.
Okay, thank you. Bye.
Well, yeah. See you then. I guess you have to go.
It was very fast.
Yeah,
I
it's
gotta
very
go.
fun.
Bye.
Yeah. See you.